Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 8 of a unit, Mechanical Properties of Fluids. So let's begin with today's class. First we will discuss a shape of the meniscus. Let's have a look. Consider a tube which is just immersed into the water. Then when we observe this situation, it has been already highlighted. We observe that the liquid surfaces bends at the meeting point. Yes. So let us understand why the liquid surface bends at the meeting point of the liquid and the solid surface. Why this kind of situation arises. So let's have a look. The situation is, let's suppose this is one of the container and this is the glass and this is the fluid that has been filled. So let's take one of the point. This is the point A. On this point all the forces are acting that we have shown here, that one of the force is the adhesive force and it is acting in this direction. It's an Fa. The cohesive forces, as we have discussed in the starting, that adhesive forces, it's the force between different objects. Cohesive forces, it is the force between the same objects. So this is the cohesive force. It's an Fc. So as we understand that there are two forces, these two forces are acting on it. One is the Fa, another is the Fc. Fa represents, it's an adhesive force. It is the case of the adhesive force, and while the Fc, it is the case of cohesive force. So these two forces are acting. Now let's suppose understand that this Fa is greater than Fc. If this was the situation, this could be the Fr, that is what we call as the resulting force due to this two. If this is the situation, that means this fluid particle is being stretched or is being snatched from this direction. It's an Fr. So what fluid is going to do is that fluid is going to bend itself, which is perpendicular to this force. This is the situation. So this meniscus will look like this if it is the boundary of the container. I hope this is clear. So this is one of the reason where Fa is greater than Fc, which is the case when adhesive force is greater than the coercive forces. You will have this kind of meniscus. When I say this kind of, you will have a concave meniscus. I hope this is clear. Now let's look at the different case. It's a surface of the liquid. It is the situation that this point A, and when this is point A, this is the adhesive force, as we have discussed in the last class, last slide as well. This is the coercive forces. Now let's understand that coercive force is greater than adhesive force. If this is the situation that coercive force is greater than adhesive forces, then this could be the resulting force. And if this is the resulting force, a surface of the liquid will always tries to be at the perpendicular to the resultant. So to be at the perpendicular to the resultant, it needs to move in this direction. So it will create this kind of surface. Yes, this is what we call as a convex meniscus. It is the convex meniscus, and this will happen with the glass and the mercury surface, in which coercive force is greater than adhesive forces. Now let's look at this. It's a third one. Let's suppose this is the particle A and this is the adhesive force and this is the coercive force, and let's suppose this is the resulting force. Let's suppose it is exactly like this. So it you will see a flat surface. This is the situation when pure water is filled in the glass container. This is the situation. I hope this is clear. Is it clear? So when which kind of force would be greater and which kind of meniscus would be there? Is it clear? I would like to add one more information with this, that this was the situation where adhesive force is greater than cohesive force, and if it is this is the case, this objects this objects whose adhesive force is greater than the cohesive surfaces will wet the surface. And when the situation is your cohesive force is greater than adhesive forces, then this objects will will not wet the surface. I hope this is clear. Now now do you understand everything up till now? Do you? Are you sure? Do you understand this? Great. Now let's look at certain quick questions. The shape of the meniscus is concave because of, yes, concave meniscus is there because Fa, that is what we call as a adhesive force, is greater than cohesive force. Next, surface tension and surface energies are blank. It's a incorrect question. Next, do you understand up till now? Do you have any doubts? Is there anything? No? Great. Now let's look at the next concept. It's a concept of angle of contact and its characteristics. So let's understand what angle of contact is. Let's suppose look at this. Suppose this is the case where a meniscus is something like this. So what we are supposed to do is to find out the angle of contact. To find out the angle of contact, what, let's suppose this is the point. This is the solid surface, this is the liquid surface. For any point to find out the angle of contact, you need to find out two tangents. First, it is on the solid boundary, this is, let's say, first tangent, and second on the liquid boundary, this is the second tangent. Angle between these two boundaries will give me the angle of contact. So it is the angle between the tangent drawn to the liquid surface and the solid surface at the point of contact. Measured, it's a measured from inside the liquid, is known as the angle of contact. And in this situation, angle of contact is the acute one. I hope this is clear. Let's look at the different situation. That let's suppose this is the liquid droplets and this is the position. Now let's make two let's make two tangents. It's a first on the solid surface and it's a second on the tangent at the liquid surface. So if I make an angle between these two, if I make an angle between these two, this angle, this theta, is the obtuse angle. So basically this is angle between tangent drawn to the liquid surface and the solid at the point of contact, measured from inside the liquid, and that is what we call as an angle of contact. So this is the situation when mercury drop is mercury drop is poured into the glass surface, and this was the case when a glass container is being filled by the water. So in this case, it's an adhesive force which is greater than the cohesive force. Angle of theta, it's an angle of contact, theta will be obtuse. And it was the case when cohesive force is greater than adhesive force, and your theta, it's an angle of contact, will be the obtuse. I hope this is clear. Is this clear? So in this case, angle of contact is obtuse. Now let's look at the characteristics of the angle of contact. Angle of contact is constant for a given liquid and solid pair, and it depends upon the nature of the liquid and the solid. So it is basically a property of this pair of a medium. It is dependent on the inclination of the solids. So for that, for a given liquid solid pair, Even a small contamination of the surface causes a large change in the angle of contact. And for a liquid which partially wets the solid, the angle of contact is acute, that we have discussed. And for a liquid which does not wet the solid, for a liquid which does not wet the solid, the angle of contact is the obtuse. I hope this is clear. As you can see, these are the dew drops. Yes, they are not going to wet the surface, so they will make angle of contact which is the obtuse one. Even this is the case with the mercury as well. So these are the cases where angle of contacts are the obtuse. And for a liquid which completely weights the solids, the angle of contact equals to 0. In this case, the tangent to the liquid surface is almost along the surface of the solid. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's look at this. If water and glass, if water and glass has an angle of contact which is less than 90 degree, if it is less than 90 degree, then this water will weight the glass. Let's look at the second question. If if angle of contact is obtuse, if angle of contact is obtuse, then liquid wets the solids? No. Depends upon the temperature? No. Liquid does not wet the solid. Yes, this one would be the correct. I hope this is clear. Is it clear? So based on the angle of contact, we have many information that whether it will weight the surface or not, which kind of force would be higher. When I say which kind of, I mean whether it would be higher side would be the adhesive forces or higher side would be the coercive forces, and every this kind of information can be determined. Now let's discuss the pressure difference on two sides of a meniscus. So when I find out the meniscus of this kind of surfaces, there exists a pressure difference on both the sides of the surfaces. And we understand, and tried we have tried to calculate, and we have tried to show what is and why this material is going to bend when it's a meeting point. So there are three types of shapes of the liquid surfaces at the meeting point. One is the plane surface, another is the concave surface, and the third is the convex surface. Now let us see what the pressure differences is on both the sides of the surface. So let's first discuss, if the surface is plane, what would be the situation? Let's suppose understood that these two are the points A and B, and they are having pulled by the surface tension T. So the forces due to this surface tension acting on two sides of the element AB are equal and opposite, and so the resulting force acting on it is 0. So if resulting force acting on it is 0, that means there is no pressure difference on the two sides of the plane. I hope this is clear. Next, if the surface is concave, it is situation something like this. Now again, if I look at this 2 points, it's a point A and point B. At point A there is a surface tension T1, and this point it's a surface tension T1. Basically this is due to this tension T, and this is the horizontal component and this is the vertical component. As you can see that this horizontal component is going to cancel out each other, and that means it is having the net downward force on the meniscus, that is T2. Hence pressure on the concave side, always do remember this, it's a pressure on the concave side is more than that on the pressure on the convex side. I hope this is clear. Let's look at this situation. if if the surface is the convex, let's take this 2 points, it's a point A and this is point B. If these 2 points are there and I need to draw the tangent on this line, then this could be said as this is T1, this is T1, this is T2, this is T2. as we understand that this T2 and this T2 are going to cancel out each other. So it means there is net upward force. There is a net upward force on the meniscus, and hence so that pressure on the concave side is more than the pressure on the convex side. I hope this is clear. Great. So now let's look at this. Consider a surface as shown, and let's suppose P and PB be the pressure at 2 points shown that this is the point PA, this is the point PB. As I can see this that this surface is on the concave side, so PA is greater than PB. This is the answer. If the surface is plane, then the pressure differences on both the sides, yes, pressure difference on both the sides will be the same. A same kind of pressure difference do exist between the bubbles too. That let's suppose this is the situation. Let's suppose this is the, what we can say, a capillary is there, and it has been filled with the liquid, and this is the height h that it has been rise. Let's call this as a, this as a b. Then what I can write, it's a PA minus PB, that is equals to 2T by R, or rather I should write it is equals to N into 2T by R. This is the situation. It's a PA minus PB, that would be equals to N into 2T by R. So as I understand that pressure on the concave side would be always higher. It's a pressure on the concave side will be always higher. I hope this is clear. Is it clear? Is it? Do you understand this? So can you answer this kind of questions? Let's have a look. Suppose the situation is something like this, that it is this kind of situation. This is point A, this is point B. So what I can write, it's a PA minus PP. Let's suppose number of free surfaces R1. It's a PA minus PB is equals to 2T by R. Let's suppose this kind of situation is there. This is D, this is C. So what I can write, it's a PC minus PD, that is equals to 2T by R. This R is the radius. R is the radius. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you understand this? Have you? Have you got this? Are you sure? Now let's suppose the next situation is that there is two bubbles. Let me redraw it. That this are the two bubbles and they are going to merge with each other. That let's suppose this is point A. This is, or let me write down the pressures. This is P1. This is P2. This is P0. So find out relations between P1, P2 and P0. Yes. So which one is higher, which one is lower? If you look at this two bubbles that are going to, or that are trying to merge with each other, then this is the concave side. As you understand this is the concave side, and as this is concave side, that could be written as P2 minus P1, that is equals to 2T by R. If you look at this two surfaces, it's a P2 and P0, then even in this is the situation where this could be seen as the concave side, and concave side pressure would be higher. So if it is a concave side, this could be written as P2 minus P0 is equals to 2T by R. I hope this is clear. So from this you can have a relation between P1 and P0 as well. I hope this is clear. Is it clear? Is it? Great. And from this concept of excess pressure, we can find out radius of curvature of new bubble. Let's suppose this is the situation that this was the first bubble and this was the second bubble. Let's say this is R1 and this is R2. If this bubble merges in a presence of atmosphere, then new radius of curvature, so new radius of curvature will be 1 by r is equals to 1 by r1 minus 1 by r2. And if let's suppose if same thing happens, if this two bubbles tries to merge in vacuum or isothermally, then the new radius will be equals to root of r1 square plus r2 square. Please keep this in mind. I hope this is clear. Is it clear? So can you do this kind of questions? Can you? Is it possible? Let's have a look. Let's suppose we have two bubbles which are, let's suppose this is 3 centimeter and this bubble is having a radius of 4 centimeter. If this two bubbles tries to merge each other in two different conditions, in two different conditions, find out new radius of curvature. So first, in the first situation, that they combine in vacuum, so it's an r that is equals to root of r1 square plus r2 square. This is equals to 3 square 9 plus 4 square 16. It's a root of 25. That would be equals to 5 centimeter. This was the first situation. And let's talk about the second situation. That in the second situation, if they combine in a presence of atmosphere, if they combine in the presence of atmosphere, then I can have it's a 1 by r is equals to 1 by r1 minus 1 by r2. So this is equals to 1 by r, which is equals to 1 by 3 minus 1 by 4. This is equals to 4 minus 3 by 12. This is equals to 1 by 12. I hope this is clear. And from this, it's an r, which is equals to 12 centimeter. I hope this is clear. Is it? Is it? Great. So let's just wind up the session over here. This was all about the shape of the meniscus, angle of contact, and excess pressure. Please revise this and attempt as many questions as possible. This will help us to get this kind of questions done. Thank you. Have a good day. Take care. Bye bye.